The next set of examples I want to talk about here for applications is something called a simple harmonic motion. And this often happens when things are vibrating. So for instance, your book talks about any sort of vibratory or oscillatory motion. So something that's vibrating or moving back and forth. For instance, the vibration of a guitar string, the swinging of a pendulum. So like if you have an old grandfather clock that, the pendulum swings back and forth like this. The bobbing of an object attached to a spring, even things like radio waves, television waves, and sound waves as well, all have this same similar motion. And they're represented by trig functions. So here's one example here. So we're going to assume that there's a spring on the ceiling for whatever reason, and there's a ball attached to it. Now what happens is, let's say you're not touching it. So the spring is on the ceiling. It's not totally loose, like it has some structure to it, right? It's maybe like a metal spring. And the rest position, where it would just stay if you were to not touch it, is called its equilibrium position. So that we can usually consider to be at 0 on an XY axis. And because the spring is hanging from the ceiling, what's going to happen is we're going to take that ball, we're going to pull it down, we're going to release it, and it's going to spring back and forth, right? This upward and downward motion. And that's what you see in this picture here. And this is sort of taking over time. Let's say it's taking like every 1 second. So you have the spring with the ball starting at its rest position or its equilibrium position, excuse me. We're going to pull the ball downward, down 4 units here. So maybe that would be inches, so 4 inches. So it's going down 4, so that's going to be a -4 for the distance, and we're going to let it go. And again, it's going to spring, it's going to go past the equilibrium, and it's going to get smaller, and it's going to go up, actually, and then come back down. And it's going to have the same motion over and over again. If you think about a spring, you release that object, it's going to keep bouncing back and forth and back and forth like this, right? And that's what you see here. Now, this is a very basic example where we're going to kind of ignore friction for now. Eventually that spring is going to stop, right? So in this picture here, we're having the same exact, and we're going to say like, okay, assume that's going on and on forever and ever. There's no friction, there's no air resistance, it's never going to stop. That spring is going to keep going forever. You would have this perfect kind of trig function. In reality, of course, it would stop over time. This distance would become smaller and smaller. And your book actually has I'm going to move down here. Your book has a really nice example of that, what would really happen. And it's still a trig function, but it's a little bit more complicated. It has this exponential multiplier with it, which shows that, that distance back and forth for the spring would actually start to slowly decrease, and it will eventually come back to its equilibrium position. So we're going to talk about the more simpler version here. Again, it's called simple harmonic motion. So we're kind of ignoring that friction piece. So, and I wrote this in our notes here. So we're going to do an example so you kind of see what's happening. And I'll show you the notes that I started. And again, this is a good time to, if you need to, pause the video and take some of your own notes down, or make a note to refer back to that picture if you need it, or draw the picture in yourself. An object that moves on a coordinate axis is in simple harmonic motion if its distance from the origin, d, at time t is given by either the function cosine or sine. So you have a cosine omega t or a sine omega t. The a here is still your amplitude. So that idea is still the same, or the absolute value of a is still the amplitude, which is the maximum displacement of the object from its rest position. So how far it moves from its rest position. The period here is still 2 pi over omega. So again, you should see a lot of similarities to things we already know. And that is the time it takes for the motion to go through 1 complete cycle. So the same definition for period. And then we also have another term called frequency, which is given by 1 over the period, or omega over 2 pi. So that's another calculation that we often see with harmonic motion as well. So one thing to note here, how do you know when to use cosine or sine? It really depends. They're the same shape function, just depends on how you start. So for instance, we're going to use the sine function. When the object is at rest at time 0. So you're starting at rest at that equilibrium point. And when you would use the cosine function, when the object is at its max displacement. So its greatest distance. From rest at t equals 0. One thing to note here as well, it depends on the direction. So we're going to see that, you know, if we're pulling an object downward to start, you're going to have a negative a value, right? Because you're moving down like we saw in the picture. Or if you're for some reason pulling the object upward to start, or your scale has a, you know, you're starting positive, then you would have an a that's positive. So we'll see that in the next example as well. All right, so I'm going to see if I can put the equation on the same page here just so we can reference it. So a ball on a spring is pulled 4 inches below its rest position. And then it's released. The period is 6 seconds. And we're going to write the equation. All right, so I am going to go to the next page to do some work, but I kind of just wanted to stay on this page just to talk through the starting point. So here we have a simple harmonic motion. And when we have a simple harmonic motion, you're going to start with either this cosine function or the sine function. Those are your only 2 options to start with. Now here we also know that the spring is pulled 4 inches below its rest position and then released. So it's starting at 4 inches below. So it's not starting at rest, right? It's starting at 4 inches below and then we release it. So at time equals 0, we're starting below the rest position. So if we are below the rest position, then we're using cosine. So cosine is when we are our greatest distance from rest. It could be below or above, it doesn't matter. We use the sine function if we start in the rest position. Here, we're not starting in rest position, so we're using cosine. Okay. Now, the other thing I know is that the spring is being pulled 4 inches below its rest position. And amplitude is the same amplitude as that up and down change, how high and low that trig function is going to go. And this is the same example that we saw in the picture. So if you're going 4 inches below, it's going to go 4 inches below, and then it's going to spring up to 4 inches above. It's going to have that same change on either side, again, assuming that we're ignoring friction and things. So your amplitude here is 4. Okay, so this is your amplitude. But our A is going to be -4 since we start below the rest position. So if you're starting below the rest position or in the negative, you know, in a negative realm, then your A is going to be negative in the formula. The other thing we need to find is we need to find the omega here. And we can go ahead and do that. We can use the idea of the period. Right, so our period is equal to 2 pi over omega. Our period here we're told was 6 seconds. So 6 is equal to 2 pi over omega. Now I really need omega, so I'm going to solve by multiplying both sides. And then I can go ahead and divide by 6. And I see that my omega is equal to 2 pi over 6, or I can simplify that to pi over 3. So those are like the 2 key pieces we need here. So putting this all together then, my formula is D equals -4 cosine pi over 3 and then t. Now we can leave it like this. If you like to put parentheses around that pi over 3t, you can as well. It doesn't matter, but that whole piece will be being plugged into the cosine. So this is how we can find our equation here. As long as we know our amplitude and our period, then we can go ahead and find any of those missing pieces, the A, and then also the omega here, excuse me. All right, let's do one more example. So let's say there is a mass that moves in a simple harmonic motion, and it is described by the equation D equals 10 cosine pi over 6 t. Where t is in seconds and d is in centimeters. So in the last example, we took the base information, we found the equation. Here we're going to do the opposite. I'm going to give you the equation and we're going to answer some questions about it. So for A, let's find the maximum displacement. We're going to find the frequency, and then we're also going to find the period. So find the time required for one cycle, i.e. the period. Now remember first, there we go. Displacement is how far that spring or object would move from rest, right? So going below and above. And that's found by using your amplitude here. So your max displacement is going to be based on this amplitude. So that's also going to be your max displacement here. So the max displacement is 10, and then just be careful, we're in centimeters. So 10 centimeters. Now to find the frequency, we did have this formula in our notes, so go back maybe another page in your notes, and we do have the formula for frequency. It's the omega over 2 pi, or 1 over the period. Well, in our formula, our omega is this right here, right? So hang on, this is your A, and this is your omega. So we have pi over 6 over 2 pi. Now, when you're solving this, I'm going to multiply by 1 over 2 pi to cancel out that denominator. And then I can just multiply straight across. So this gives me pi over 12 pi. And of course, those pi's are going to cancel. Just be careful, there is something on top. There's always a 1 there. You can't just put the 12 up top. So it's 1/12 is our frequency here. So the frequency is 1/12 of the cycle per second. Or oscillation. So your frequency is always that part of a cycle that occurs in 1 unit's time. So here we're talking about seconds, so that's why I'm doing seconds, but it's 1/12 of the cycle or the oscillation, whatever you want to call it, here per second. And then the last one is going to be the period. I'll use a different color here, I guess. So for your period here, it's going to be 2 pi over omega. So 2 pi, again, your omega is pi over 6. So you multiply by 6 over pi. So I get 12 pi over pi here. Now 12 is in the numerator, so it's fine to just leave it as 12. It's only if the value's in the denominator, you have to be really careful. And our answer here is 12. You can also find the period by taking 1 over the frequency. So you can see that they are reciprocals here, which is okay. It's supposed to be like that. So our period here is 12. So the time required for 1 cycle is 12, and it's seconds here. So whatever your units are, seconds.